cordic algorithm is based on a rotation matrix. Now this is the rotation matrix here. We will go ahead and we'll prove this in the rest of the video, but before we do that, let's go and look at an example of using it. So this is the matrix here. What it does is it takes one point x naught y naught and it multiplies it via this matrix here, and we get another point x1 y1. And you can see here with this example, so we've got our y and our x-axis, we've got a point x0 y0 which is 2, 1, and we want to rotate this point anti-clockwise by 90 degrees. So the length here is exactly the same as the length here. So in effect it's rotating it round in a circle. Now in order to do that, we use the rotation matrix. So we're looking for the new point x1, y1, and it's going to be the cos of the angle we want to rotate it. Now we'll just use degrees here for simplicity. So it's going to be cos of 90 and minus sine of 90, sine of 90 and cos of 90. So that's just this rotation matrix here, and we've replaced the angle phi with the angle we want to rotate by, which is 90 degrees. And we're going to multiply that by the original point x naught y naught, which is along 2 and up 1, so that's 2, 1. Now this matrix here is the same as this matrix because the cos of 90 is 0, the sine of 90 is 1, so it's negative 1, cos of the sine of 90 is 1, and the cos of 90 is 0. So we multiply this out via matrix, so it's 0 times 2 is 0, and it's minus 1 times 1 will give us the minus 1 for the x. We've got 1 times 2 will give us 2 for the y coordinate. So that's going to give us a point minus 1, 2. So we're going to use this rotation matrix throughout the rest of the course. So let's go ahead and we'll show you why that works, and we'll prove this rotation matrix. Now this diagram looks a bit busy at the moment, So let's take our time and we'll talk our way through it. We're going to have a y coordinate and we're going to have an x coordinate. We've got a vector here and the end point of this vector is point x0, y0. And we're going to rotate this vector through an angle until the x0, y0 goes to a new point x1, y1. And the length of this vector is r, and the length of this vector is r. So in effect we're just rotating this point here, x0, y0, in an anti-clockwise direction around a circle until it gets to the point x1, y1. Now, the angle for the original vector is angle theta, and the angle between the original vector and the new vector, that is the extra angle we're going to add, is going to be the angle phi. So angle phi is from here to here, and angle theta is from here to here. So let's go ahead and we'll look at some of the lengths that are involved here. This angle theta, opposite the angle is this length here, so this is going to be the opposite, and this length here would be the adjacent, and this length would be the hypotenuse. So we know that cos of theta is going to be the x0 upon r, so this is the opposite over the adjacent. So therefore we can say that x0 is equal to r cos theta. So x0 is just this distance from here to here. So we can say this distance here on this little triangle is r cos theta, and I've drawn it in there for you. Now we can do the same for this length here. We can say that sine theta is going to be the opposite over the hypotenuse, which is y0, that height there, divided by r. So we can say that y0 is equal to r sine theta. So this height up here is r sine theta. So we've got this distance here, and we've got this distance here, and they're r sine theta and r cos theta. Now we're interested in the second triangle here, and the distance x1, which is the distance from here to here. Well, that distance x1 is going to be given by our r cos theta plus phi. And the y1 is given by r sine theta plus phi. So we're going to use two trig identities. Now, I haven't proven the trig identities here, but I will leave a video in the appendix section with the proof of these identities. So we've got our x1 is equal to r cos theta plus phi, and we can expand that as r cos theta cos phi minus sine theta sine phi. So this is the trig identity, which I'll prove in the appendix section. So we multiply that out and we get this line here. And now we know that the r cos theta, well, r cos theta is nothing other than the x0 value. So we can replace that with x0. And you notice that r sine theta, well, r sine theta is nothing other than the y0. So this gives us the first part of our matrix. Now again, we can look at the y1. y1 is r sine theta plus phi. And we can use the second trig identity, so that's the same as r sine theta cos phi plus cos theta sine phi. And we can multiply that out and we get this here. And then we know that the value r sine theta, well, r sine theta is nothing other than y0. And we can see here that the r cos theta is nothing other than the x0. So we have the second part of our matrix here. So I have rewritten the two results here. We have x1 equals x0 cos phi minus y0 sine phi, and y1 equals y0 cos phi plus x0 sine phi. And when we rewrite that in the matrix form, we get the rotation matrix here. So now we have the rotation matrix. We can go ahead in the next video and we can start looking at the cordic algorithm. So thank you for listening. I'll get you on the next video.